x cubed over x plus 1 squared. So f of x cubed over x plus 1 squared. We know that this function has a slant asymptote because the numerator has degree 3 and the denominator has degree 2. And when I divide them, I will get degree 1, which means a line, which is the slant asymptote. So this is the only type of rational function that has a slant asymptote, the one that has a degree by 1 unit higher in the numerator than the denominator. Good. So in order to find the slant asymptote, I have to divide x to the third by x squared plus 2x plus 1. And I know that this is x. X times x squared is x cubed. I subtract. X times 2x is 2x squared. I subtract. And x times 1 is x. I subtract. Negative 2x squared minus x. X squared times negative 2 is this. Negative 2 times x squared is negative 2x squared, but I subtract. Negative 2 times 2x is negative 4x, but I subtract. And negative 2 times 1 is negative 2, but I subtract. And I cannot continue. And this is the line in question. So f of x, in other words, I'm saying that x cubed over x plus 1 squared can be written as the quotient plus the remainder over the divisor. And as we discussed, at infinity, this is 0. Why? Because the degree of the numerator is 1 and the degree of the denominator is 2. This will be way more powerful, and this will approach 0 at infinities only. That's why this is the slant asymptote. Slant asymptote y equals x minus 2, which means that it looks like this because it has a positive slope. So the whole function will come from negative infinity and go to positive infinity because it has to follow the slant asymptote. If the leading coefficient were negative, then I would have said it's coming from positive infinity going to negative infinity. But no, the leading coefficient is positive, so it's going this way. So when I start my table, I no longer need to determine the limits at infinity. Because I have them here. Clearly, negative infinity to infinity, because it has a leading coefficient that is positive. So I will make myself a note, y equals x minus 2, slant asymptote. I have to put in the domain, and I know that this function cannot be defined at negative 1, which means x equals negative 1 is a vertical asymptote. Then when I plug in 0, I get 0. There's nothing else other than these two limits. So at negative 1, the numerator is always negative. But the denominator is always positive. Because even if I'm on the left, even I'm on the right, it doesn't matter of negative 1. Because this is always positive. If I'm left or right of negative 1, this is always negative. So both sides are negative infinity. At this point, I've exhausted the function. That is done. X and y intercepts, limits, if there is a vertical asymptote, limits left and right, and behavior, everything is done. Now, which is not a friendly function, but we have to look at these sometimes, right? I have to study the derivative, the first derivative, critical numbers, whatever, and put them in here. And then I move on to the second derivative. This is not a friendly function to differentiate, like what we just had. Okay, So I'm going to copy it here, x to the third over x plus 1 squared. So y prime, 3x squared times x plus 1 squared minus x to the third times 2x plus 1 over x plus 1 to the fourth. I cannot stress enough, if you start distributing, you'll never get anywhere. Please. I'm going to factor out x squared and x plus 1. From the first term, I have x squared out, and I have one of these out. But I still have 3 and one of them. So I have 3x plus 3. From the second term, this is out. 2 x's are out. So what is still left is negative 2x. Again, I cannot stress enough. If you start distributing all this in here, you're never going to get anywhere. The only chance we have is to pull out everything, and look what happens. It's so easy now. So 3x minus 2x is x, or x plus 3. It will never be undefined because the function is undefined at -1, but it will be 0 when x is 0 and when x is -3. I study the sign. Let's see what I don't want to study the sign for. I don't want to study the sign for this. Who cares? It's positive. I will also rearrange the function, at least in my head, or writing it down like this. I split cubed into squared, and because I don't want to spend our precious time on these two. They're always positive. Who cares? It will not change the sign. So when I plug in -10, -10 with -10 will be positive. When I plug in -2, positive and negative. If I plug in -0.5, right here, -0.5. With -0.5, positive and positive. And with 10, positive and positive. Now is the moment of truth. Because I have to plug in the function -3 to get this first. So f of -3. -27. -3 plus 1 is -2. -2 squared is 4. And this is approximately -7. -27 over 4. Okay. So now I have to make sure that these two are working well together. If not, I'll say, uh-oh. From -infinity up to -27 over 4. Correct. Down to -infinity. Correct. From -infinity up to 0. Correct. From 0 up to infinity. Correct. Okay, now, do I want to differentiate this? No, I don't. So I'm going to use, so this is always increasing. So it could be increasing this way, or it could be coming from the vertical. Okay. Let's differentiate it. Wow. Oh, so I'm differentiating this. That I will change into x to the third plus 3x squared over x plus 1 cubed. I know what's going to happen here because it has a maximum, right? So local max. So it has to be negative. It has to look like this. I know that for sure. I'm not 100% sure here, but I think it's going to do this. So I think all this will be positive. But, okay. So, top prime, 3x squared plus 6x. Denominator, x plus 1 cubed minus x cubed plus 3x squared times 3x plus 1 squared times the inner function prime, which is 1, over x plus 1 to the 6th. Do not distribute. It will be a terrible mistake. Okay. So I will factor out x plus 1 squared. And it's still a lot. Over x plus 1 to the 6th. Okay. I took 2 out, but I still have 1. So I need to distribute this in here. So 3x to the 3rd. Watch me run out of room. Plus 6x squared. Plus 3x squared. Plus 6x. Okay, this is out. So I have minus 3x cubed and minus 9x squared. I did not run out of room for the first time ever in history. Okay. Oh, thank you. Oh, thank you. Brilliant. Ah. Awesome. I did not expect that. So the second derivative is 0 when x is 0. Okay, fine. What else? So this is always positive. To the left of 0 is negative, and as expected, to the right of 0. Oh. To the right of 0 is positive. Okay. IP. Wow. Okay. It better be nice, the graph. At least that. So I don't need anything but the table. Everything else is useless. Gibberish. Nothing. When we graph functions with asymptotes, we have to start by graphing the asymptotes. That is absolutely mandatory. So we have x equals -1, and the function is not symmetric. I should have mentioned that. It cannot be symmetric with a slant asymptote like this and a vertical asymptote x equals -1. So now I have to graph this. When x is 0, y is -2. And when y is 0, x is 2. Y equals x minus 2. Okay, next. I need -3, -7 roughly. 1, 2, 3. 1, 2, 3, 4, 5, 6, 7. First piece, very clear. From -infinity, opening down, increasing to the maximum, and reaches the maximum, and it comes back asymptotically closer and closer to the corresponding vertical asymptote. Very clear. First piece is done. Now let's see here. So from -infinity, opening down till the origin, and increasing, increasing, opening down till the origin, where it changes concavity, opening up, getting closer and closer to the asymptote. Wow. X to the third over x plus 1 squared. So opening up from negative infinity to this point down to negative infinity. From negative infinity on the right-hand side of the vertical asymptote, opening down till the inflection point, where it changes concavity, because it's an inflection point, still increasing towards infinity, opening up. It has to follow the slant asymptote. So please do not graph something like this. No, it has to follow the slant asymptote. It has to follow the slant asymptote. It has to follow the vertical asymptote. It has to follow the vertical asymptote. It turned out to be a very interesting one. Why? Because look how nice this came out to be. And I didn't really want to find that second derivative. And actually it was quite nice. Any questions? Any questions? Okay, anything else? Anyone?